Swayam Prabha. Digital India. Educated India.
Good morning. We have been looking at the development of finite element equations for 2D problems involving only one variable. So we have discussed this in the last lecture, how to develop the equations for a triangle. And these are some of just a few equations, not the elaborate complete set. I just put it down for the sake of completeness here. And if this is the basic governing equation, and it's in relation to the heat conduction problem, because here we have the temperature, we have the flux boundary condition. And so this is a weak form. So we have the weighting function W, and then we integrate it. And then a part of that has been cancelled with this one and leaving only this. And then we also have WIQ d omega. So this is the Q is the heat source within the body, something like some electrical conductors which are there. So we discussed at length why we choose the triangle element, and then we have choosing this approximation within the element as the shape functions ni, nj, nk, phi I, phi j, phi k are the function values at ijk node, right? And where ni, nj, nk have been obtained in terms of ai, bi, ci, aj, bj, cj, and ak, bk, ck, which I gave last time in the last class. Please refer to that when you want the exact expressions for all these a's and b's and c's. So just again to recall the first equation. So, and first equation, if you put Wi is equal to Ni, for example, in this equation, right? So then what we get is that when you take the derivative here, and phi hat itself is this one, phi hat you substitute into this one, and then if you this one, dou Ni by dou x will be that of Bi, and then this involves, if you take the derivative, is Bi phi I plus Bj phi j plus Bk phi k. So that's what this is. And then this one will be that of Ci, right? And then this involves the Ci fi and Cj phi j and Ck phi k. So this is what we did last time. And then if you put that into this and collect the terms phi I, phi j, phi k, so this is the equation that it looks like this one. So only thing that was not completed towards the end of last thing is the right side of this equation. In the right side of this equation, so we have Wi times Q integrated over omega, particularly the element here, right? And then, so let's look at that. So that's what Niq d omega integrated over the element here. So this is the element. And also we have another term, Niq bar d gamma. So this is also necessary to be investigated. So let's look at this Niq, and this is Ni is a function of xy, and Q may be a function of xy, but without loss of generality, we can assume Q to be constant as it is at the center of the element. Okay. So this is also true because when the element becomes smaller and smaller, the value of Q may not be varying very much over the element. So there's nothing really wrong. So looking at this one, d omega or dx dy over the element here. So taking q to be constant, so it's essentially ni xy integrated over dx dy. So let's look at the variation of ni. Of course, taking here, taking q as constant. Okay, so this is IJK nodes. And then let's look at what Ni looks like. Ni, we shown it last time. If you're showing it as an isometric view, so it looks like Ni has a value of 1. This is a small tent kind of thing with the pole of Ni being 1 here. Okay, Ni being 1 here. And so that means that at every point here, you have a certain value of Ni, which is the height of this one. So this is the integral of this one is nothing but the volume under the tent here. So that is nothing but Ni so this is nothing but volume under the surface. Under the surface as shown in the picture, right? So we know that anytime you have this kind of things, so it is nothing but 1/3 of the area multiplied by the height h here, which is 1. So it is actually where A is the when you have this kind of solid here. So this is just like a cone, for example. If you have a cone, then the volume of the cone is nothing but area of the base multiplied by the height of the cone, right? So exactly the same way here also the volume of this under the surface here, as it is shown here, is nothing but 1/3 times area times the height. That's 1. So like that, so we have here, so that means that we have Ni times Q times over the volume of the element is nothing but Q times A. Of course, under the assumption that Q is constant. Okay. So like this, so obviously the same thing is also true. Right now I can say same thing is true. We will use that for Nj and Nk in the sense that Q times Nj is the same as Q times okay, they all become QA by 3. So which we will be using a little later. Okay, so then we also have this Ni Q bar time. I will just tell you that what is this? This has to be integrated over gamma q. Let me show you that here. Okay, so one more integral is there, Ni consider Ni q bar over gamma q. So this has to be understood very carefully here. This has to be done. So for example, if you have a omega like this, and here we have this part of the boundary we call as gamma q. So q bar is the heat flux coming out of this surface, right? So if you have, so this is all gamma q here, only this surface. And if you have one element here, I, j, k. So if you are looking at Ni and then trying to integrate it over this boundary, gamma q, so what is the value of Ni on this boundary here? So this is the gamma q boundary where the heat is leaving. So if you recall, so what will be the shape of the function here on gamma q? So if you, then there are so many other elements here. Let's say there are so many other elements here. But our consideration is over this element. So what is the value of Ni? So if you look at the value of Ni as far as this element is concerned, so Ni has a value of 1 here, so which I was showing here. Here, Ni has a value of 1 here, and it comes down to 0 here and 0 here. So this is, so that means that here you will have a value of 1, right? I mean, if you draw it, you have a value of 1 here, and it goes to, slowly it goes to 0 here and 0 here also. What about beyond that? So beyond that, as far as this Ni for the element is concerned, so it is only defined over this element. So that's why we call it as piecewise defined functions, where the function is non-zero only over this element. And that's what we discussed in the last class in one dimension. So we know that Ni is just on that element, and beyond that element, it turns out to be 0, right? So as far as this element is concerned now, so Ni is, if the element is here, then Ni is 0 by the time it comes to gamma q. So let's say if ijk are very much interior, in omega, I mean away from gamma q, then realize that Ni is 0 on gamma q. Okay, so this you should realize that if it is, this element is interior away from gamma q, then the value of Ni is only defined over this element, and away from this element it becomes 0 as far as this Ni of the element is concerned. Beyond that it becomes 0. By the time it comes here, definitely it is 0. So this is what you have to realize, that as far as this element is concerned, Ni is 0. So this will turn out to be, if so, if so will be 0. So this contribution is going to be 0, right? However, there are other elements here. So you should also realize that if you have, maybe I'll draw it here again. So on this gamma q, so there is an element here. This is an interesting element. So this element has, again, if this is the gamma q here, for this element, for this example, okay, so here Ni is 0 on this side, okay, so Ni is 0 on gamma q, okay. So let me just write it down here, okay. So as far as this is concerned, just like earlier, if the element is on the boundary, as shown here on the boundary, gamma q, as shown here, right? Here, this is I, this is j, this is k here, and Ni again here, again Ni is equal to 0 on gamma q, okay. So the point is interior. On the other hand, if you look at for the jth node, okay, so the nj xy q bar on gamma q, okay. So as far as this element is concerned, we are only concerned with this element. There may be some other elements also, so we are not at this moment concerned. So if you are looking at, this is jth node, and what about this j, which is right on jth node, on lying on gamma q, then what is its contribution then? Nj times, so if you look at again, so this is I hope this is a isometric view. I hope you're getting the picture here. So this is Nj, right? So Nj is what? Having a value of 1 here at the node 1, and then we are only concerned along Jk, okay? We are not really concerned how it is going to happen here on the other side. Maybe it looks like this. Okay, so as far as Jk is concerned, where we have heat leaving this one. Okay, so if you are integrating this now, Nj along gamma q, then Jk falls on this gamma q, and then you have to integrate it. So you have to integrate it j to K, this and J, right? So you have to go from J to K, and at Nj it is having a value of 1, right? Here. And then if you integrate it from this to this, then it will be a value of Sjk by 2. Sjk is the side length. Side length, and this is Sjk, and integration is of course by half, and you have q bar. Okay, so now for the, if you are talking about the weighting function as Nj, then this contribution will come to be Sjk by 2 for this element. Remember, any element which is very much inside, there is no contribution. On the other hand, just now I'll ask you this question, is that what about if you take the weighting function Nk? If you take weighting function for Wi is equal to Nk, if you do that, then Nk times q bar. So this also has to be integrated between J to K, and this also Sjk by 2 times q bar. So for, just to recall again, so for the node J, it is Sjk by 2 times q bar. For node K, if you just look at this one, so it also will be like this, right? At K, it has a value of 1 and then turns out to be 0 at this point. So if you integrate it over Jk, it's again Sjk by 2 and times q bar. Okay. So like this, so this integral over gamma q has to be carefully done only for those elements who have their side falling on gamma q. Otherwise, if the element is very much interior, then you don't have to worry. Okay. So now coming to finally this equation as what we have done there, bi squared plus ci squared by I bi bj plus cij by j and bi bk and this side you have what is that, qa by 3 and minus, well, I leave that here, ni q bar okay, I'll leave it there. Okay, so this is using Wi is equal to Ni, using Wi is equal to Nj. We have similar equation. Last time I already indicated. So that's second equation, and the third equation will be taking the weighting function as Nk and simplifying. So we get BK BI CK CI YI BK BJ CJ CK plus PK square plus CK square is QA by 3. So the last integral, I just left it like that. But then, depending upon whether IJK falls on the gamma Q or not, you have to accordingly take that into consideration. So in a nutshell, if you want to put it, this of course this K is also there. Please include that K, which is thermal conductivity. This K is thermal conductivity, and this element here looks like this. Okay, just I'm writing it down in the form of a matrix equation, nothing more than that. So this multiplying phi I VA by 3 Okay, so this is the final equation of the element. So where this is the matrix, we used to call it as K matrix by itself. And please don't get confused with this K. And then multiplying these are the temperatures, phi I, phi j, phi k. And this is the heat source term. And this one you have to accordingly include if any of the element edges are falling on gamma Q. Okay. So you also have to remember that this is elemental equation, and to really solve the complete problem, so it has to be assembled into the bigger system equation. So that means that these go IJK nodes or IJK degrees of freedom, and that means that this is II, IJ, IK, this is JI, JJ, JK, and KI, KJ, KK. So these are the locations where it has to go. Okay, so this is how the elemental equations are done, and then how it is assembled and all that. maybe we can see it as an example when we take it up in the next class. There's one last thing which I have to tell you is about the one important aspect is the continuity. So if whenever you talk about the element and all that, you recall, so important aspect is the this we have been telling it should be phi hat has to be C naught. This is what we have been telling. So this is particularly true so for example, this phi e is defined on this element, and there is another phi e is defined on this jkl. So phi e, so let us say sigma e and sigma e plus 1. So this phi e and phi e plus 1 are defined separately for each element. So the important consideration which we have to satisfy is that we know that this phi e is ni phi I and nj phi j. This is for the element e, and so similarly for e plus 1 we have j, k, l and j and k and n. So these are defined separately for each element. So what is the guarantee that, so when you go from element e to e plus 1, when you cross this border jk, inter-element boundary, are you sure that you are going to have the same function value? So that means that here in this element and here in this element, are they exactly same? Okay, so this is true and it gets satisfied is because this element here has if you look at that one, this is the variation of the element from phi I, phi j, phi k, and it's a linear distribution. So similarly here, similarly on element e plus 1, it is the phi e plus 1 goes forward like it's a linear variation. So you can very clearly see here that along the side jk, if you find out the value of phi is same, so phi e is equal to phi e plus 1 on here in this example on side jk, because you have a phi j and phi k here, right? And it's a linear variation. So the same linear variation is also used for element e plus 1. So thus this linear variation of the element of the approximation function for each element is satisfying the requirement of C naught continuity, as well as, of course, that it is once differentiable within the element. Okay, so we'll stop at this moment, and in the next class we will take up an example so which will illustrate all these ideas. Bye.